So we're going to talk about regression and correlation. And in doing that, what I want to do is kind of emphasize something that I think is really important and is lost on a lot of stats classes and a lot of analytics classes, is that what we're about telling the story of the data. And that's really an important statement, and I want to be clear about this. Statistics is a field created by mathematicians. In their world, there are a lot of really interesting and important things in a stats book. In my world, most of it isn't. So what I'm trying to do with you, and what I do in analytics myself, is I try to say, what's really important for the story? What's really important to know and be able to explain to people as you move forward? A lot of what mathematicians teach in a stats class is really important. I mean, I'll give the mathematicians their due about what's important in mathematics. But oftentimes when it comes down to a business analysis and being able to explain what's happening in a business problem, a lot of what the mathematicians want you to do and pay attention to really has no bearing and really doesn't matter. So what we're going to do in this class and how we're going to move forward is I'm going to emphasize to you the things that matter. Now, I'm not ignoring the mathematicians. Some of my best friends are mathematicians. But what I'm doing is I'm saying we need to kind of focus on what's important for business. And so that's the really key thing. And so if this were an in-person class, you would be sick of me walking up to you and say, what are the big four questions? And I say this in particular because it's one of the few things I can honestly say I've made an honest contribution, original contribution in my academic career, in saying statistics consist of four big questions, particularly at this level, particularly at this kind of beginning level. As you go up in a bunch of levels, it gets more complex in different ways. But there are only four questions that you're really concerned about for most applications and most business questions. Here they are. Are these things different, and how do you know? In other words, things are not the same, and how do you know? That's one question. Are these things related, and how do you know? And we look at relationships. And those are like the two big things to remember. Am I looking at things that are different and trying to figure out if they're different, or am I looking at whether or not things are related? Those are two separate questions. We use different tools for those, but that's really what you have to know most of the time. Is what you observed what you expected? This is hypothesis testing. So you've probably done hypothesis testing in another class. You set up a null hypothesis. That's what you expect to happen. You expect the null to happen. And if it does, great. But then if it doesn't, you suggest the alternative. And that's what that question deals with, is what you observed, what you expected. The last one is how good is your estimate. And for every statistical test, you get a test statistic and a p-value, and it tells you how good your estimate is. When you do a confidence interval, it tells you how good your estimate is. All of these things, because everything's an estimate, you don't have any exact numbers in statistics because it's fraught with error. Everything else is an estimate, and you have to explain how good is your estimate. This is it. This is an entire stats course in one bundle. I was giving a talk at the University of Nebraska several years ago, and I was talking to some grad students, and it was fairly informal, and we're just in a room, and I rattled this off, and this poor woman just said, "I am just really angry," and I said, "Why?" And because I was like, "What did I do?" And she said, "That is everything I was supposed to learn in statistics in 5 minutes." And it really is the case. And so if you keep this framework in your head as we move forward, please remember, and I will refer to it in different places, but I'll come back at this a number of ways. And so this is the framework for you to think about. All right. what we're about with correlation and regression is, are these things related, and how do you know? And what we're interested in is we're interested in the relationships, right? We're interested in saying, as this thing changes, what happens to these things? And so that's what we're interested in correlation and regression. And that's the story we're going to tell. As one thing happens, what's the other thing that's happening? In other words, that's what you're about in correlation and regression. We're going to talk about correlation first. There's the formula, and it's actually it's not as bad as it looks. I haven't calculated one of these since the 1980s, but I remember doing it. The computers do the heavy lifting for you, and so just to make sure that you know that we are going to be doing hypothesis testing, and these are the general rules for hypothesis testing. And I'm going to switch slides here because it's a little bit more readable. You're going to create a null and alternative hypothesis for all of these things. You're going to figure out which statistical tests you're going to use, and for that you're going to use the big four questions. Am I looking at relationships? Am I looking at differences? You're going to compute the test statistic. You're going to run the data, right? You're going to, in this case, you're going to run correlations and regressions. You're going to determine what the rejection value for the null hypothesis is. For the most part, we're going to use 0.05. If you use 0.05 for everything, that's fine. You'll be okay. There are times where you might want to say 0.1. There might be times you want to say 0.01. There are times even in my field where I want to say 0.2, but those are really weird times. But generally speaking, if you use 0.05 as your cutoff, P is 0.05, and P is less than 0.05 as your cutoff, that works for every possibility that you could do. The nice thing is that SPSS will compute the test statistic for you as well as the p-value, and so the computers do the heavy lifting for you. What you're getting, that compared the obtained test statistic value to the critical value, that is you're saying, is it above 0.05 or is it below 0.05 for p? And then you decide whether you're going to reject or fail to reject the null. And remember that you aren't accepting the null because you still have doubt because there's error in the system. So don't say I accept the null. You want to say I fail to reject the null and I'm suggesting the alternative. If the obtained test statistic, you're going to reject it or fail to reject it. All right. So we're going to talk about correlations, how they work. We're going to talk about computing a simple correlation. There are also demo videos on this as well, how to interpret it, and what other types of correlation tests exist. So remember that a correlation is a relationship between x and y. As x changes, how does y change? The values are from 1 to -1. A perfect correlation is 0. You're trying to look at change, and so in this case, what we're looking at is how does height increases, what happens with weight. And remember that it's not a perfect relationship, right? This is a relationship that has a lot of things going on in it, and as you look at it, if you drew a line here, you would have things that are over and under on both of those things. All right. Scatter plot is a core idea in this. You plot your x's and y's. We've done that before. In correlation words, this is a perfect correlation. This would be R equals 1. R is the correlation test statistic. R equals 1 in this case, and so that would be a perfect correlation, and it's a perfect positive correlation. Sometimes as x increases, y decreases, and that would be a negative correlation, and so this would be a positive, a perfect negative correlation. And correlations in the real world do a lot of different things, and so this particular correlation is on socioeconomic status and grade achievement. And so these are all the school districts in the United States, and what it basically says is that there's this really strong relationship between wealth and educational achievement. It's not a perfect relationship, but it's pretty strong. The other thing is that you can find, you can go online and look at this and look at and actually download the data from Stanford, which is the source of the study. And it's fairly interesting. And it's fairly interesting to begin to run that against different variables in a correlation or a regression. So SPSS will allow us to test the significance. And so here's the thing about every test I want you to run. I want you to report the test statistic first and then the p-value. And so in this case, the test statistic is R, and the p-value is the significance in SPSS. And so you would report R, in this case, R equals 0.07. P is, in this case, when it says 000 like that, P is less than 0.001 is how you would report that. And that would be the relationship between age and the amount of time it takes to get to work. The nice thing about correlations in SPSS is it actually tells you at the bottom whether or not it's significant or not, which it's the only test in SPSS that does that. I'm not sure why, but it will do that, which is convenient. Oftentimes we want to think about correlations as particularly for regression, I try to think about all the variables that I might use and pick out the ones that make some sense. And I'll run a correlation matrix, and one of the videos shows you how to run a correlation matrix. And what you get is and you can kind of think of this line here as like a mirror. What's above this line is the same as what's below the line, and so that correlation of 0.077 is the same here and same here. It's the same relationship, just in a matrix. But again, it gives you a sense about, okay, what correlations are strong? 0.9 would be strong. What correlations are moderate? What correlations are weaker? And you can kind of get a sense about, okay, what variables might I want to use in a regression analysis or something like that? And I get a sense about that in a correlation matrix. And you will run some of these as well. So, in thinking about correlation, the only thing it says what is the strength of the relationship, and you're saying I either have a strong relationship or I have a weak relationship or somewhere in the middle. And if you look online, you will find a whole range of variations on what's strong, weak, or moderate. People will give different cutoff points. I'm not going to quibble over, like, if you're 0.5 and you say, it's a weak relationship, or if you've got like 0.3 and you say, it's a moderate relationship or whatever. I'm not going to quibble over that too much, as long as you don't kind of identify 0.3 as a strong relationship. This is a nice guideline. This is probably the one that I like the best and the one that I use with students the most. So with that, take a few minutes, pause the slide here, and just look at which relationships are strong and which relationships are weak, which relationships are positive, which relationships are negative. I'm not going to pause here, but you pause. There's some other things to talk about as well, and how much the relationship is really explaining. And so if you square R, you get R squared, and that's the percentage of variance in one variable that is accounted for in the other variable. That will become more important in regression. We'll talk about R squared as explaining the amount of the dependent variable. That's where that becomes stronger. But the stronger the correlation, the more variance is explained, and so that's an important piece. You're also going to have unexplained variance. And so if you're explaining 30% of what's going on in your problem, you're leaving 70% on the table. That's okay. You just have to recognize that and know that and be able to say that out loud if someone asks you about that. So just know that if your R squared is 0.3, you're explaining 30% of what's going on, this coefficient of non-determination is 70%. That 70% is being explained by something else, and we don't know what it is right now. We may look for it, we may not. All right. Big thing about correlation is correlations do not mean causality. And I say that quite seriously, is that because two things happen at the same time doesn't mean that one's causing the other. And so this is an important concept to kind of think about. I harped on it one so much during a semester that students actually gave me a coffee mug that said correlations do not mean causality. I got my message across, in other words. But some examples of this is that these are not necessarily causative factors. And so one of the things is that when you talk about correlations, you really are only talking about that there is a relationship, but one thing isn't causing the other. And that's a fine line for a lot of people. If you can make that twist in your mind, you're okay. If you can't think of something being related or correlated without thinking about it causing the other thing, then that's more problematic. Some other ones, just so you see that. I often do this in class and spend some time on it. This website's a little bit fun with some of its spurious correlations. And spurious correlations are those correlations that make no sense at all, such as ice cream sales and crime, because ice cream sales increase when crime increases, and so you make the judgment on that, because I'm not going to say we should stop selling ice cream. All right. Remember that all correlations do is they talk about the strength of the relationship. They do not talk about causes the relationship. So that's the piece of a correlation. All right. You're going to use Pearson's correlations for most of the things we're going to do, but I want to let you know that there are other measures of correlation. Spearman's is one, and it uses ranked data. You can use ranked data. There are different ways. It comes out very close to Pearson's. I like Spearman's a lot. It just potato. I use Pearson's. The phi correlation is also used, and I don't use it at all, to be honest with you, but I want to make sure you know that it's out there. All right, that's correlation. So the next thing is I want to talk about regression analysis. And one of the things about regression analysis is that it allows us to begin to talk about what's happening in terms of complex relationships. And so if you're trying to think about predicting prices or predicting what will happen or predicting sales, regression analysis is a really good tool. Now, you can't predict the future, right? But if you look at past performance, if you look at patterns that exist, you can begin to kind of say, well, if this happens, maybe this will happen. And if we increase here, that seems to have some kind of effect here. And so working that through is how a regression would work. And so one of the simplest forms of regression is this notion that your high school GPA predicts your college GPA. And there's a lot of studies that will say that there's a strong relationship here. It's not a perfect relationship, and so one of the things is that it is, however, a fairly strong relationship. And so using that allows colleges and universities to kind of say, okay, they did well in high school, they're going to do fine here. What you want to do is you want to think about how you're going to create this prediction. As X changes, what happens to Y? And you want to try to think about that direct relationship. And so what we use regression analysis. And it assumes a direction of an effect. In other words, there's an independent variable that allows a dependent variable to change. There are lots of flavors of regression. We're just going to use one. You'll see a bunch of them when you use SPSS. You'll see a whole list of them. We're just going to use linear regression. You could go your whole life with just knowing linear regression. If you want to get into deeper stuff, into deeper waters, that's fine. But for now, and for the purposes of grad school, linear regression will do you just fine. In fact, for most of your professional career, it will do well. We're going to do some bivariate regression, meaning you have one independent variable and one dependent variable, and some multiple regression, where you have multiple independent variables affecting one dependent variable. And so we're going to do some of those, and some of the other videos will show how those work. All right. All your variables should be, from an independent samples. They're normally distributed. And so that's an important piece. When you get errors, they should be normally distributed. We'll look at some of that. Linear regression makes several assumptions. Number one, that there is a linear relationship. If there isn't, your regression will probably collapse on you, which is okay. When we talk about interpreting regression in another video, I'll say if your regression doesn't work, that's okay. You just have to explain that it doesn't work. It assumes that all your variables are normal. It assumes that they're not collinear. And so here's the thing, is that a collinear variable would be something like this, is that I have a variable for family income, and I have a variable for personal income, and I'm trying to predict spending. Well, those are probably all collinear in some way, because if you have more money, you spend more money. So that's a problem right there. But family income and household income probably are collinear as well. And so what you're trying to do is try to avoid both collinearity and autocorrelation, which means that you're really measuring the same thing. You get really high R values, and in chemistry or biology, really high R values are really good. In business, if I get an R value above 0.7, I get suspicious. If I get an R value in the 0.9s, I usually think I've done something horribly, horribly wrong. So be cautious about high R values. Always remember these assumptions. When you're doing a regression, try to think of independent variables. Try not to have variables that are measuring the same thing. All right. We talked about the coefficient of determination, the R squared. We talked about that before. That's going to tell you how much of the variance you're explaining. When I go through the interpretation of this, you'll see that again. You'll see it again later in this video as well. So R squared ranges from 0 to 1. Again, for most business applications, R squared is between 0.1 and 0.5 are probably where you want to be for most of your models. A little above, a little below. I'm not going to worry about that. You just need to explain it. And remember that when you describe it, you describe it as a percentage. So if my R squared is 0.3, I'm explaining 30% of what's going on. All right. The basis of a regression is a scatter plot again, just like correlation. But in this case, we have a line of regression. In other words, we're trying to make predictions along this line, so that if X is 2, Y is like 2.1. That's the prediction. And so you're trying to make a prediction at every point along the line. And we do this for the college GPA thing. But here's the thing. In this case, we have over-predicted. There's an error in prediction. So above the line, we have over-predicted. We have under-predicted, rather. We predicted here, the scores here. We're under-predicting. I always get that messed up. Here we are over-predicting. And so the error in prediction is called a residual. And we can measure residuals and look at them in different ways. It's the same equation from algebra. Y equals bx plus a or mx plus b, depending on who you had for math. And to be honest with you, my 10th grade algebra teacher, she told me that equation would be important in my world, in my life. I did not believe her at all, and really is the primary equation that I do most of my analysis from and most of my work from. And I'm not a math major, right? I'm not someone who loves math. I'm someone who loves analytics, but not necessarily math. All right, so that's the basic theory behind it. And again, equations, we're not going to worry about them. But what we're trying to do is we're trying to predict how good the prediction is. And so that's what we're about in our regression. We're looking at how good is our prediction. We're going to do some measurements on it. And remember that just like we talked about at the top of this particular piece, is we're going to run a statistical test. We're going to walk through these steps, right? And we're going to write null and alternative hypothesis. And so I'm going to give you a quick example of this. So the null here, I've got there is no relationship between household income, age, sex, and usual number of hours worked in Colbert County, Mississippi. And there is a relationship between income, age, sex, and usual number of hours worked in Colbert County, Mississippi. And what I've done is I've got data from Colbert County, Mississippi. And the first thing I want you to look at is I want you to look at whether your model is significant or not. And SPSS is going to print out this thing. And again, I go through this in a separate video as well. This is the test of your model. This says whether or not you have a relationship here. And that's an important piece. So whether or not you're going to reject the null or suggest the alternative is this. If you find that there is a relationship here, you would reject the null. If you find there is no relationship here, you would fail to reject the null. So the thing that you're looking at here is F. That's the test statistic. So F equals 7.621, P is less than 0.001. P is less than 0.05, that's the cutoff point. And so because P is less than 0.05, you would reject the null. If, let's say, F was like 1.2 and P was like 0.4, you'd fail to reject the null. But in this case, you're going to reject the null. And so one of the things I can't emphasize enough is you have to tell me what the test statistic is and what the p-value is. That is really important. The nice thing about ANOVA's, about the regression piece, is that it reminds you what your dependent variable is and what your independent variables are. All right. Once you've done that, you go to the R-squared and you explain and you say how much is your model explaining. In this case, R is 0.11. You're explaining 11% of what's going on. R-squared, I'm sorry, I just blew that. Just rather than retake that, let me fix that. R is 0.1. You have a really small relationship going on. So that's the size of the relationship. R square is 0.014, and that means that you're explaining 1.4% of what's going on. Really not a very strong model. In fact, one of the things that if you came up with this model, you would look at your client and say, you know what, this model we have here, not very predictive at all. We need to go back to the drawing board and find a new model. Then we want to look at our predictors. And one of the things that we're looking at is we're looking at the beta values. So we're looking at this particular column here. And one of the things I will start off with is the constant. The constant is theoretical. And so I would say don't worry about the constant at all. It is theoretical, and I want to make sure that you know that. It is the y-intercept. This value is the y-intercept. So in terms of household income, it would be $63,000 in terms of a dependent variable. But as age increases by 1 year, You go by the unit. Age increases by 1 year. Household income increases by $237. As the usual hours of work per week increases by 1 hour, household income increases by $431. Sex is a bivariate variable, so it's 1 or 2, and as this is coded, so men are coded as 1, women are coded as 2, and you can use these. They're called dummy variables, where you just have 2 options. Don't use a lot of them, but you can use them, and sex is often used for these because there are differences in how men and women have access or are affected in a regression analysis in different ways. In this case, men are coded at 1, women are coded at 2. So as you move 1 unit from, changing from men to women, there's a decrease in household income of $3,259. So that would also indicate that women in households are being paid less, and that would be a result that you would talk about. You also want to say whether or not the variables are really explanatory. And so to test that, we test that with the t-value. And this is the p-value that looks right. P is less than 0.05, the variable is explanatory. If p is not less than 0.05, it's not explanatory in this model. And I emphasize in this model because a lot of times if you adjust the model in different ways, you can make it explanatory. So in this model, here t is 2.3, p is 0.02, it's less than 0.05. This is an explanatory variable. The same thing for usual hours worked, it's an explanatory variable. In this case for sex, it's not an explanatory variable. And it's hard to say why or why not, because usually most studies will indicate significant relationship between sex and pay. To be honest with you, when I ran this, I'm not sure why, but I know that in this particular model it's not significant, although there's a lot of research, and I would encourage anyone who's interested in looking at gender pay, go look at it, because it's really good data and good to look at. The collinearity statistics are all good. They're all within parameters. Collinearity, VIFs, you're looking for things that are above 5 and usually above 10 for this. For collinearity, if it's below 0.25, for tolerance, it's a problem. These are all fine. And I said 0.4 here. It depends on who you're looking at. I think when I wrote this slide, I saw some 0.4, but it's 0.25, 0.4. You'll also find a lot of differences on the internet, and that's one of the things about this. But generally speaking, collinearity is one of those pieces that you need to pay attention to. All right. With that said, it's about telling the story of the data. So the story of the data here is talking about age having an effect on household income, and the number of hours you worked having an effect on income. And that's the story that you want to tell. And always remember that you've got this equation here, but you're really trying to tell the story of the data. And answer the big question: are these things related, and how? And so in a regression, you determine whether there's a relationship, and then you explain what that relationship is and whether that relationship is meaningful in different ways in doing that. That's really what regression is about.